Hey guys, today we're going to talk about another theorem, so the intermediate value theorem, which means that most of your work today is the answer to the problem. These are kind of a little bit like proofs. So let's first talk about what this theorem is and what we can do with it. So this is the intermediate value theorem. It says if f, the function, is continuous on some interval a to b, and k is any number between f of a and f of b, then there is at least one number c in that interval such that f of c equals k. And I think it's a lot easier to see this when it's drawn out. So if we have some coordinate grid and I have some value a and some value b that I have a continuous function on. And remember, continuous functions just mean that I can draw it without picking up my pencil. So if I have something that goes from here to here and it can do whatever it wants in between, as long as it's still a function. That was a little bit iffy, but as long as it's still a function, we're good. So now I could name a function value for both of those pieces. This would be my y value that corresponds with a, and this would be my y value that corresponds with b. So what this theorem is saying is it's saying that if I pick any number in between a and b, so if I pick some number c, that there has to be some k value that goes through on that point, and I believe I picked this right. Because in order, if this function really is continuous, in order for it to get from a to b, it's going to have to cross this point at c. So that's all it's saying. You have to cross all of the y values in between these two x values in order for it to be a continuous function. So this function also guarantees that there's at least one number in there. So if you had something that looked like this, where it did some crazy stuff. Ooh. This is still a function, it's still continuous. I didn't have to pick up my pen in between, but I can see here that there are actually two values that would have equaled k. So this theorem just guarantees that there's at least one of them in between those two values. So again, all this is saying here is that if I'm looking at some continuous graph, there are numbers in between the numbers they gave me, and we can guarantee it based on this theorem. So let's see what we can do with this intermediate value theorem. Okay, so we're going to use the theorem to show that this polynomial has a 0 on 1, 2. So remember, these are x values. This is an interval of x values including 1 and 2. And what this is saying here is we know someplace on this graph that y equals 0, because remember, a 0 is a root or a solution or an x-intercept. So the first thing I know is that this function is in fact continuous. Okay, it's continuous because it's a polynomial. And we talked about that on the day of continuity. If it's a polynomial, if it's sine, if it's cosine, if it's an exponential, they are continuous on their domain. And so when I look at this, I know that it's going to be continuous on this thing because it's continuous everywhere. So what I'm going to do is I'm going to prove that there is a number in here that would give me 0 for my y. And in order to do that, I'm going to plug in these two values. So I'm going to figure out what f of 1 is, and all I have to do for that is wherever I see an x, put in a 1. And if I did that math, I would find out that that was 1 minus 3 plus 1 minus 1, or negative 2. Okay, then I'm going to do the same thing for the other end point of my interval. I'm going to find out what f of 2 is. So I just plug in 2. And if I had 2 to the 4th minus 3 times 4 plus 2 minus 1, that would just get me positive 5. And I think it's easier to see if you saw this on a graph, because if I'm looking at these points, I have 1 and 2. And then I know that I'm going down to negative 2 for this first point, and then I'm going up to 1, 2, 3, 4, 5 for the second point. So in order for me to get from point A to point B, I would have had to cross the x-axis, which means I'm guaranteeing there's a 0 in there somewhere. Now I'm not saying where the 0 is, I just know that there is some 0 in here. So what I've just proven is that negative 2, a negative number, is less than 0, is less than 5, which means that there's got to be some value, there we go, some function value in there. There's some c in this function that would give me 0. So this is all you have to show for your work. You have to prove to me that if they're asking you for a certain value, that yes, in fact, my function values do bookend that one value in there, and that you definitely do have some number in there that would give you 0 for your y. Okay, so because it went from negative to positive, or it could have gone from positive to negative, we know that it had to cross the x-axis, therefore there's definitely a 0. Again, it's like a proof. So if you were someone who wanted to box all your work, it would be literally this entire thing. Okay, let's do one more example. We're going to use the intermediate value theorem to find the value of c guaranteed by the theorem. Now what this means, it doesn't mean I'm going to say c equals a number in the end. We're just trying to find the interval on which c should exist. So what I'm going to do here is, first of all, I know that this is my interval. So this would be my first value, my a, and this would be my second value, my b. And I'm going to plug those two values into the function they gave me. Now the hard part about this problem is the fact that it's a fraction. And so, you know, you fraction haters, you'll have to get over it. But all I've done here is I've plugged in 3/2 wherever I had an x. And so now I just get to do some arithmetic here. So I know that if I square a fraction, I have to square both the top and the bottom. And when I'm multiplying fractions, I just multiply the tops and then the bottom. So this is actually 3/1. So I'd have 9, 3 times 3, over 2 times 1. Okay, I've got to find common denominators in order to multiply these, or sorry, add these things up. So the first thing I'm going to do though is multiply this 2, again 2/1, so 18/4. And if I wanted to find a common denominator, that would be 4 here, which would mean I'd have to multiply the second one by 2. Okay, same deal on the bottom, got to find a common denominator, which would be 2. Now I'm just going to do some regular math. 18 plus 6 is 24, all over 4. And then I have 7/2 if I do that with my common denominator. And then I can just do my regular fraction stuff here. If I have this guy, I would keep my first fraction, flip my sign, and change the fraction. And then I can try to simplify as much as I can. So this is 2, this is 1. So I'm left with 24/14. Yep. Which could then simplify to 12/7 if I divided everything by 2. Okay, so I get my first fraction there, and something that might be a little bit helpful here is to figure out what this would be as a decimal point, because I'm not really sure where 12/7 is. This is about 1.7 if I think about it. I know it's a full and then almost to 2. Okay, now I've got to do the same thing with my second point, and I've got to find f of 3. So wherever I see an x in my original equation, I just plug in 3. And thankfully this one's a little bit easier, less fractiony. I get that this is 18 plus 3, that's 9 times 2, all over 9 minus 1 is 8. So my second value is 21/8. And again, that as a decimal is really close. It's over 2, it's about 2.6. Okay, so what I've done here is I needed to prove that the function values in between these two x's had a 2 in there. So it was in between, 2 is in between those two numbers. And so if I looked at this, 12/7 or 1.7 is less than 2, is less than 2.6, which means that I have a c value that's in between these two values. So c is in between those two x values that I started with. And so what I just did there is I guaranteed that c value is in between those two fractiony numbers. I didn't say that c is equal to something, but I know it should be somewhere in between 3/2 or 1.5 and 3. Okay, and that is how you use the intermediate value theorem. Okay, it's a proof. It's all about figuring out what each of the interval values are, and then showing that these guys are actually in between. And since for this case 2 was in between the two function values, I knew for a fact that c had to be somewhere on that function or on that interval. I will see you tomorrow.